In this video I'm going to go through and prove the first 5 of the circle theorems that we need to know from the syllabus, and they're not in exactly the same order as they are in the syllabus, but I think they're in an order that makes sense in terms of proving them. So we need to be able to prove these, and we need to be able to use these then to find lengths and angles, and maybe even then to prove other results which follow on from these. Obviously it's completely arbitrary how these are numbered. But like I say, there is probably a logic to numbering them in a certain way. So I'll show you the 5 theorems first of all, and then I'll do a quick proof for each of them. So the first one, theorem 1, the angle at the center subtended by an arc of a circle is twice the angle at the circumference subtended by the same arc. A little bit of language there that we need to understand. You'll notice too that I've also put a little coded symbol there that we often use to represent this particular theorem, just so that we don't have to write it out in full. So when we talk about something, an angle being subtended by an arc, if you consider having a circle here, and we've got maybe an arc on that circle. So now there are actually 2 arcs, aren't there? When we put 2 points, there's a major arc and a minor arc. So normally we mean the minor arc if we were just talking about arc AB, and we could talk about angles being subtended by that arc, and the 2 main ones that we talk about would be an angle at the circumference subtended by that arc. So that angle could be anywhere on the circumference subtended by that same arc, and the other one that we might talk about is an angle at the center which is subtended by that arc. So there's only one of those. Okay, the angle at the center subtended. So it sort of means, spanned by that arc. Alright. Now let's go through then and consider the other theorems. Just have to get rid of that stuff I did there. So theorem 2, an angle in the center, or an angle in a semicircle rather, is a right angle. So every angle in a semicircle is a right angle. Theorem 3, angles at the circumference of a circle subtended by the same arc are equal. And again, for each of these I'm just giving the little symbol that we sometimes use for those. And then our next couple, theorem 4, the opposite angles of a cyclic quadrilateral are supplementary, so not equal but supplementary. And finally, theorem 5, chords of equal length subtend equal angles at the center and conversely. Alright, now this video is probably going to go a little bit longer, but I'm going to try and do a proof for each of these. And these will often use, well, they might just use angle properties. Some of them might use congruent triangles. So first of all, how can we show that the angle at the center subtended by an arc is twice the angle at the circumference subtended by the same arc? Let's get ourselves a circle to work with here, and so we'll get let's make this our points A and call that B up there. This point here can be C, and so then we're saying that the angle at the center, which is subtended by arc AC, is twice the angle at the circumference. And so the first thing we're going to do is to extend a line through, or from B through the point O. Extend BO, let's say, through the point O to the point D. So let me add another line on there. I might grab another color and just add a line that extends through there. And then let's call this angle in here X, and that one in there Y, just to save us a little bit of time there. So we're letting angle A BO be equal to X, and we're letting angle C BO be equal to Y. Alright, now what we've got from that center, of course, is that any length from the center to the circumference is a radius. So AO is going to be equal to BO, which is going to be equal to CO, because they're all radii or radius lengths. And so then what we have in these two triangles that we've created is that the angle that is sort of external, so let's say angle, I didn't label point D, did I? Let's label D there. So angle AOD is going to be equal to 2 times x. And let me just explain why that's the case. So I'll get another color. So we're saying this angle out here, AOD, is equal to 2 times x. And the reason for that is that that is also x. Angle A there is also x because that's an isosceles triangle because they're both radius lengths. So that's because equal base angles in an isosceles triangle, and then also our theorem which says the external angle of a triangle is equal to the sum of the opposite interior angles. So 2 lots of x are equal to angle AOD, and by the same logic we can say that angle COD is equal to 2 times y. So that's again using the fact that the other side triangle is an isosceles triangle because CO and BO are radius lengths, and so therefore this angle here is also y, and that means that the external angle is equal to 2 times y. Alright, so what we have then is that if we were to say the entirety of angle AOC, which is that external angle, so AOC is equal to 2x plus 2y, well that's equal to 2 lots of x plus y, which is 2 times angle ABC. Alright, so the angle at the center, which is 2x plus 2y, is equal to 2 lots of the angle at the circumference, which is just x plus y. Alright, that's the first one. Now some of these are a little bit quicker, so let's go on to the second one here about the angle in a semicircle. Draw ourselves a circle here. Let's put a diameter across there, and then get ourselves an angle. Alright, so once again let's label these as A and B and C and the center at O. And so now we've actually got an angle at the center at AOC. So if I'm talking about, let me put another point on here just to be clear, so on arc ADC, which means this arc around here, because if I just said arc AC I could mean either direction, but I mean that direction there. So on arc ADC we can say the angle at the center, AOC, is equal to 180 degrees, and that's because it's a straight line, isn't it? So the sum of any angles on a straight line will be equal to 180. Well, by theorem 1 that we just proved, we can say therefore angle ABC is going to be a half of that, a half of 180. So that's by theorem 1, which we just proved, which is equal to 90 degrees, which is what we were trying to prove. So we've proved that angle ABC will always be 90 degrees. Alright, theorem 3, angles at the circumference of a circle subtended by the same arc are equal. Let's get ourselves a proof on that one. So let's set up a situation here where we've got an arc, and we'll make this that point B and point C there. So on that arc AD, the arc from A to D, we've got two different angles at the circumference, angle B and angle C. So let's let O be the center of the circle, and let's draw in that. Alright, so by theorem 1, if we call that one x and that one y, then x is going to be equal to a half of angle AOD. That's by theorem 1, that has that little symbol that looks a bit like a kind of arrowhead. But also angle y is going to be a half of angle AOD by that same theorem. Okay, so we're basically saying angles at B and C, the x and y values there, they are both half the angle at AOD, half the angle at the center. So therefore, angle x is equal to angle y because they're both a half of AOD. And so therefore we've shown that any angle at the circumference subtended by that same arc is going to be equal. Alright, 2 more to go. The opposite angles of a cyclic quadrilateral are supplementary. So let's prove this. Draw ourselves any cyclic quadrilateral. Make sure it's, it doesn't sort of look like it's too regular, so that we can show this is true for any. And let's let O be the center of our circle. Label these points on the circumference A, B, C, and D. And so let's join up, say, those ones there, and we'll let this angle be X and this angle be Y, and show that they are supplementary, that they add to 360. Now, here we need to be clear about which arcs we're talking about. So let's talk about on arc BCD first of all. So that means going around kind of the right-hand side of the circle from B to D. So on angle BCD, we could say that angle BOD, so there's 2 different angle BODs we could consider. There's that one, and there's also this one, isn't there? But because we've talked about being on arc BCD, we mean the yellow angle BOD that's showing there. So by theorem 1, we know that that angle has to be twice this angle at the circumference. So therefore angle BOD we could say is equal to 2 times x. And then on arc BAD, so that's going around the kind of left-hand side of the circle, angle BOD is equal to 2y. And this time we're talking about this angle BOD being twice that angle at the circumference. Now both of those are by theorem 1, so let me just indicate that here. So both of those are by theorem 1, which is saying the angle at the center is twice the angle at the circumference subtended by the same arc. But we also know that angle BOD plus angle BAD is equal to 360 I should say, because it's a complete revolution. So is equal to 360 because it's the angles in revolution. Therefore 2x plus 2y equals 360. Now really I actually made a mistake there, didn't I? It's not BOD and BAD, it's BOD and BOD, which is a bit confusing, but I guess I mean the 2 different ones. So maybe it would actually be better just to say straight away, let's leave out that line there, and let's just say 2x plus 2y, since they were the letters that we used instead. Therefore, 2x plus y is 360, and therefore x plus y is just 180, which is what we wanted to prove, that the opposite angles in the cyclic quadrilateral were supplementary. Alright, good job for hanging in. The last one here, Theorem 5, the chords, that chords of equal length subtend equal angles at the center. And conversely, we could say angles at the center that are equal subtend chords of the same length. So we're going to prove it this way around, but you could then try and do the converse where you prove the converse. Okay, so let's draw ourselves a circle with a couple of arcs of equal length on it. So let's say there's one, and let's say that one there. Let's make it a chord. They look roughly equal. Okay, so let's say that one's AB, and this one here is CD. I probably should have gone in one order or the other, shouldn't I? So if I'm going around in that order, let's call that CD. So let's let AB and CD be chords of equal length. And then we've got O is the center. So then all of these lines from the center to those points are going to be equal, aren't they? So OA equals OB, which is equal to OC, which is equal to OD, because they're just all radius lengths. So therefore we've got two triangles that are congruent by SSS. So therefore triangle ABO is congruent to triangle C DO. Doesn't really matter too much which order we put those in, and that's by SSS. And therefore angle at the center AOB must be equal to corresponding angle COD, because they're corresponding angles of congruent triangles. Now, like I say, you could have a go at proving the converse, which is starting off with the angles being equal and showing that the chord lengths therefore have to be equal as well. But I think that's more than enough for one video now.